Hi, myself Aryansh Kumar Singh, entry number 2021 CS10113. I'm here with my ELP 101 lab project. The project is based on op-amps, that is operational amplifiers. So let's begin. What is an operational amplifier? An operational amplifier is an analog circuit block that takes a differential voltage input and produces a single-ended voltage output. Op-amp usually have three terminals, two high impedance inputs and a low impedance output port. Moving on, operational amplifier classifications. There are four ways to classify operational amplifiers. First, voltage amplifiers take voltage in and produce a voltage at the output. Second, current amplifiers receive a current input and produces a current output. Third, transconductance amplifiers convert a voltage input to a current output. Fourth, and the last, trans resistance amplifiers convert a current input and produce a voltage output. The key characteristics and parameters of an op-amp. There are many different important characteristics and parameters related to op-amp. These characteristics are described in the slides below. Open loop gain. The open loop gain of an operational amplifier is the measure of the gain achieved when there is no feedback implemented in the circuit. This means the feedback path or loop is open. An open loop gain must be exceedingly large to be useful in itself except with the voltage comparators. Voltage comparators compare the input terminal voltages. Input impedance. Another important characteristic of an op-amp is that they generally have high input impedance, Zn. Input impedance is measured between the negative and positive input terminals, and its ideal value is infinity, which minimizes loading of the source. In reality, there is a small current leakage. Output impedance. An operational amplifier ideally has zero output impedance set out. However, the output impedance typically has a small value which determines the amount of current it can drive and how well it can operate as a voltage buffer. Negative feedback and closed loop gain. In an operational amplifier, negative feedback is implemented by feeding a portion of the output signal through an external feedback resistor and back to the inverting input. Negative feedback is used to stabilize the gain. The closed loop gain can be calculated with the equation V out over V in is equal to 1 by F. Operational amplifier configuration topologies, that is, their applications. There are several different op-amp circuits, each differing in function. The most common topologies are described below. Voltage follower. The most basic op-amp circuit is a voltage follower. This circuit does not generally require external components and provides high input impedance and low output impedance, which makes it a useful buffer. Because the voltage input and output are equal, changes to the input impedance equivalent changes to the output voltage. V out is equal to V in. Moving on. Inverting operational amplifier. In an inverting operational amplifier, the op-amp forces the negative terminal to equal the positive terminal, which is commonly ground. Therefore, the input current is determined by V in by R1 ratio. In this configuration, the same current flows through R2 to the output. Ideally, the current does not flow into the operational amplifier's negative terminal due to its high Zn. The current flowing from the negative terminal through R2 creates an inverted voltage polarity with respect to V in. V out can be calculated with the equation V out is equivalent to minus R2 over R1 into V in. Op-amp applications as an integrator. Op-amp is used as an integrator also. The integrator op-amp produces an output that is proportional to the amplitude of the input signal as well as the duration of the input signal. Instead of a resistor in the feedback loop, we have a capacitor. It is able to perform the mathematical operations of integration as the output varies with the input and duration of the signal. Op-amp application as a differentiator. Op-amp can be used as a differentiator as well, where the output is the first derivative of the input signal. V out is equivalent to minus RF into C into dV in by dt. The following equation gives the relation between the input signal and the output signal. As you can see, the output Voltage is a first derivative of the input voltage. At last, I would like to discuss the advantages of the operational amplifiers. There are many advantages to using an operational amplifier. Operational amplifiers often come in the form of an AC and are widely available with countless selectable performance levels to meet every application's needs. Op-amp have a broad range of usages and as such are a key building block in many analog applications, including filter designs, voltage buffers, comparator circuits, and many others. In addition, most companies provide stimulation support such as PSPICE models for designers to validate their operational amplifier designs before building real designs. So that's all I have collected related to op amps. I hope I have covered all the basic details. Thank you.